So today's lecture is related to what's called k-means clustering, and we're going to tie that into what are called Gaussian mixture models. So last time we talked about, well, okay, so let me kind of back up a second. So we're going to spend most of our time in this class doing what are called supervised learning problems, right? Meaning where we have data and we have labels, and we're trying to get our machine learning algorithm to predict the labels as well as possible from the data, right? But there are also a lot of other situations where before you even go down that path, you're trying to kind of look for structure in the data to find out whether there's anything that you can pick out without even having any labels, right? That's what's called unsupervised learning, okay? So the common problem we're going to talk about today is, what's called clustering, identifying clusters or groups of similar data in general multidimensional space. Now, most of my illustrations today are going to be in 2 dimensions, just because it's easy to draw and easy to show you in code. But in general, we're going to be doing this in multiple dimensions. And when I give a homework problem on this, we're probably going to be doing it in multiple dimensions too, right? And so the idea is, what are clusters? The idea is that I see, some data here, and I see some data here. To your human eyes, you would say, okay, these are 2 clusters, right? That's kind of like an easy case. A harder case may be something like, this, where, maybe it's all kind of one big blob, but, there's a little bit more overlap between the clusters, right? So kind of, there's easy cases and there are harder cases, okay? And so what we want to do is, first as a user, you decide how many clusters you want to look for in the data, right? 2 or more. And then you basically run an algorithm to decide how should I assign each point to a given cluster and kind of what represents a given cluster, right? So let's talk about this a little bit more formally. So the idea is that we have n data points. Let's call them x1 through xn in d-dimensional space. And what we want to do is we want to find k clusters, okay? Right, where here, k is, set by the user in the initial way that we're going to talk about this. And so what does it mean to find these clusters? Kind of what it means is I want to find basically a center of each cluster and then membership of each cluster, right? So if I go back to my picture here, kind of what I do is I want to say, okay, I'm going to find a blue center, and I'm going to find a red center, and I'm going to say all you guys here are in the red cluster and all you guys here are in the blue cluster, right? That's kind of what the output of this algorithm should be, is a set of cluster centers and a set of memberships, okay? So being more kind of formal about that, this is like saying, i.e., we want to find a set of k, what we call cluster centers. Let's call them, mu1 through mu k. Each of these things is in d dimensions also. And an assignment of each of the n points to one of the clusters. You have to belong to exactly one of the clusters. And so how could we represent this assignment? Well, one thing that we could do, for example, is to say I have a kind of an indicator variable gamma that is 1 if point n is in cluster k, and 0 otherwise. So this gamma for each point is basically just like a binary vector. where only one of those elements is 1 and the rest of the elements are 0, right? So it looks something like, you know, this. This is like saying, okay, if I had 6-dimensional space, or if I had 6 clusters, this is like saying that this point is in cluster number 3, right? Another way of thinking about this vector is what's called one-hot encoded. And we'll talk about that more later on, but this is also known as what's called one-hot encoded, meaning that you have a vector and only one of those elements is turned on, i.e. hot, and the rest of them are turned off, okay? Okay, so when I say I want to form a clustering, you know, what makes a good, you know, metric for how points should be clustered together, right? So kind of like the innate, you know, the kind of intuitive thing is saying, okay, I want to assign points to cluster centers in such a way that the distance is minimized in some sense, right? The distance of me to my cluster center, if I sum that up over all the points, would be as small as possible, right? So let's write that down. So our objective function would be something like this. Let's call it J. This says I sum over the number of points, and I sum over the number of clusters, and I say if point n is in the kth cluster, I want to measure the distance between point n and the cluster center k. Right, so it's basically like the sum of square distances of the points that are assigned to each cluster, okay? And so this is an unsupervised learning problem. I write that down explicitly, even though I said it already. That is, there's no ground truth labels. There's no target membership in the clusters. It's just basically, I'm looking at some unstructured data and I'm trying to find some structure in it, okay? Okay, so how could I minimize this cost function, okay? I mean, I have a bunch of stuff to minimize. I have to minimize kind of simultaneously where the cluster centers are and what the memberships are, right? And a clever way of doing this is to not try to solve the whole problem at once, but to kind of seesaw back and forth between assigning points to clusters and then updating the cluster centers and kind of keep on doing that until things converge. That's what this process of what's called k-means clustering is, right? So we can minimize J, and let me just say, you know, this is what's called a local minimum. We'll talk about optimization next week, but basically, you know, we can definitely get to a point where as we keep on alternating these things, nothing is changing anymore, and we know that's a local minimum of the cost function, but there's no guarantee that we're going to get like the best clustering. And in practice, as I'll say again, you know, what you do is you kind of cluster a bunch of times from a different random initialization, and you find the one that works the best, right? So we can do a local minimization via an iterative process called k-means clustering. Okay, so the process is super simple. So first what I'm going to do is I'm going to just kind of take k randomly initialized points in this d-dimensional space, and I'm going to call those my cluster centers, okay? So kind of step 0 is to initialize the mu k with, you know, d-dimensional vectors. You know, I could just choose random vectors, or I could kind of be a little smarter and do some sort of like attempt to kind of spread these vectors out uniformly in d-dimensional space. So now I have some initial mu k's. Then what I'm going to do is I'm going to then alternate between two steps. And I'm going to give these steps names that right now are not going to make sense, but we'll talk about in the second half of the lecture why there's a connection. We're going to call the E step is to minimize j with respect to, and a lot of times you'll see me spell this or abbreviate this as WRT just to save time. So minimize the objective function with respect to the, assignments, keeping the mu k fixed. And then the m step is the opposite. Minimize j with respect to the mu k, keeping the gammas fixed. And then, basically, I iterate until the value of j stops changing significantly. Or, you exceed some maximum number of iterations, right? So if you're writing some sort of like a numerical algorithm where you don't know when it's going to converge, you basically have two stopping criteria. Either you have a tolerance that says, okay, nothing much is changing, my improvements in my estimate are negligible, or you say, okay, I've gone for 1,000 iterations and I'm going to stop so my code doesn't run forever, right? So very simple idea, kind of just alternating back and forth between these two things. And like I said, the reason I call them E step and M step will be clearer in just a minute. And it's much easier as an optimization problem to try and do these two pieces, which are each simpler, than try and do the whole thing at once. Question?
Oh, is the iterating only for the M step? Or
No, the iterating basically is I keep on bouncing back and forth between these steps, right? I do this, 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 this. I keep on doing that until I stop. So let's just say iterate E and M steps, just to be clear. Yep. So let's think about what the solutions to these problems are, right? So the E step is basically saying, I want to find the best memberships given some fixed cluster centers. And so the natural thing to do is just say, well, I'm just going to assign you to whatever cluster center you're closest to, right? That's going to minimize this thing. So let's just say that the E step, if I write this out in some detail, is just saying that what I should do is assign this to 1 if xn is closest to mu k and 0 otherwise, right? That's just like updating the memberships. Conversely, if I have a bunch of points, the memberships are fixed, and now I want to estimate what's the best cluster center, well, the natural thing to do is just to take the average of all the points, right? That's just like, okay, what's the best thing that represents all these points? It's the mean of the set of points. So I should update my cluster center as the sum over all of the points that belong to my cluster, what those values are, over this, right? This is basically like, this number here is the number of points that are assigned currently to cluster K, right? So this is basically like the average of the, X currently assigned to K. So that's basically what k-means means, right? The k comes from the number of clusters. And I'm basically, the means part comes from this m step, right? Because I'm basically finding the mean value of the points, right? And so this process, we can show it converges because at every step I can only make my life better. I'm always reducing my cost function, right? So like I said, this will converge to different assignments for different initializations. So in practice, what I should do is, cluster several times and pick the best one. That is the one that has the lowest value of this j. Okay? All right, so let's take a look at some examples. So first of all, let me pause and ask. Any questions or comments about the procedure? Yes?
So the center doesn't necessarily need to be a point in the cluster?
What is that?
The center of a cluster doesn't necessarily be
Right, the center is not going to be one of the points. The center is going to be some other point that we assign, right? Yeah, so there's certainly, this is just some other point out there in d-dimensional space. Yes?
So the clustering you made is going to be always some sort of circle in 2D, or can it be?
Well, technically what it is right here is it's just a location and a set of assignments, right? There is no contour that encloses the points necessarily. I mean, you could draw a contour around the points. And what I'm going to do in this numerical example is you'll kind of see what the shapes of the clusters in some sense look like, right? So let's do an example to make that a little more explicit, right? So here I have a, let's make a new MATLAB notebook. Okay, takes a minute for the kernel to start up here. So what I did was I made a couple of examples before class, just like easy, medium, and hard cases. So these are not like built into MATLAB or anything. I did this as a class illustration. What's wrong with you? Yeah. Copy, paste. Yeah, there we go. So I have a couple of different levels of examples. And these are all 2D examples, but it'll work in other dimensions too. And also this, all right, so let's execute this. I guess I actually probably have to start up the kernel while it's doing this. All right, so now let's just take a look at, so the workhorse function in MATLAB is called k-means, right? So if I do help k-means, I see that there is a MATLAB function called k-means that basically I supply x, I supply k. What comes out is basically the indices of which point belongs to which cluster. That's idx. And then the c is basically where the cluster centers are, okay? And then it could also return a bunch of other stuff. Like if I wanted to, it could return, the distances to the points. And then there are a bunch of, levels of, options that I can supply. We're just using the vanilla k-means clustering here in this thing. So I wrote basically a wrapper around all this stuff to show you some examples, right? So if I cluster the easy case, right? Let's take a look at that. Oops. How did I write this function? What's in it? So, oh yes, I need to supply what kind of function. So this cluster ill is an illustrative function that does not exist in MATLAB that I wrote myself. But you can write your own wrapper around it, right? So here's kind of like the easiest case of clustering, right? The black points are my data points. The yellow dots are the converged cluster centers. And then the red and green kind of shaded areas in the background kind of show if I were to now look at any point in the plane and ask which cluster would it belong to after I was done, I would get these sets, right? So anything on the green side would go with the bottom cluster, anything on the red side would go with the top cluster, right? And if I were to redo the clustering, again, it's kind of hard to compare. Well, actually, yeah, it's not so easy to compare because it's redrawing the figure. You'll see it more clearly in some other examples. The line that I get between these two, clusters is not always going to be the same line because it depends on where I randomly initialized those yellow dots, right? And so that's something that we'll see more clearly when I use a different method of clustering later in the lecture. Yeah, but this is the basic idea. And if I have a different set of clusters, right? So here, if I use my, medium set of data, my medium set of data looks more like this, right? So here, it's a little bit less obvious, like what the cluster centers should be, or even if there should be more than one cluster, right? So I could think about drawing like kind of one big box around here, or I could think about splitting it in half, or I could think about splitting it 3 ways. The question of what the right case should be is what's called model selection, and we'll talk about that not necessarily today, but later on. Right now, this is more like a user-specified thing. And then the hard case that I made is kind of another blob where you might say, okay, this data, looks like maybe I need more than 2 clusters to represent it. So if I supplied 3 cluster centers instead, what I would get would be, something that looks more like this, right? Where I kind of split the data into 3 ways. And it kind of looks like it has these kind of like 3 lobes of data, right? Now, of course, like I said, this is all unsupervised, meaning that these data points are not labeled. If I knew under the hood that these data points were labeled like class 1, class 2, class 3, then that would be a different problem that we're going to talk about in some detail in the rest of class, which is basically like a classification problem of trying to get our machine learning algorithm to agree with the labeled classes. Right now, this is more like just kind of like unstructured discovery. Now, one thing to notice here is that the way these clusters are shaped is basically like kind of like straight line divisions between things. And if you're a computer scientist, maybe you know what's called like a Voronoi diagram. Like you basically talk about like all the points in the plane that are closest to a certain point, and it makes this kind of like tiling looking thing. So this is kind of a known reason why these lines between these clusters are straight, right? So this is kind of like what I'm going to get, but and k-means clustering is not a bad thing to do initially, but I'm going to show you next a slightly better way of thinking about the problem, right? Okay, so one thing that you don't see here, and I'm not sure I can easily get it out of the k-means algorithm in MATLAB, is kind of showing the initial cluster centers and how they move around. I mean, you could write a little for loop around this and kind of take a step-by-step through how the cluster centers move. So I came across k-means clustering probably professionally because I'm an image processing guy, right? And so k-means clustering is something that often gets used in things like, image segmentation, right? So there's a MATLAB demo that I just basically am calling here from the command line that has to do with segmenting like a stained biomedical slide, right? So for example, here, maybe I get this as my medical image, right? It's like a microscope slide that's been stained with some sort of a dye. And then what I want to do is I want to kind of cluster this into different colors, right? So what I could do is I could put each color into 3-dimensional space, for example. And in this case, it's just a kind of a picture of 2-dimensional space. Basically, this A star, B star space, if you're an image processing person, is kind of like a color space, basically. And I'm throwing out the brightness of the color. So you can see that if I were to look at this kind of like Nike swoosh shaped thing and do k-means clustering, I could get 3 clusters, and the interpretation then of going back and saying, okay, what points belong to cluster number 1, right? The cluster number 1 points would look like these kind of purpley points, right? And cluster number 2 would be like these kind of whitish points. And cluster number 3 would be like these pinkish points, right? So I'm not necessarily having to devise any sort of like explicit image processing rule based on RGB colors to segment the data in this way. I'm just kind of saying, okay, I'm going to look at this data. I'm going to say, well, these are roughly pink, purple, and white. And I'm going to run k-means clustering to find out where those points are, right? And then I can do some sort of further image processing to say, okay, now, for example, I know that this blue cluster is something that I'm interested in because maybe the cell nuclei that I want are these dark blue things. And so then I could do some further analysis just on the points in cluster number 1 and say, okay, find me the darker colored objects in cluster number 1 would be something like this, right? So then I'm doing some further like kind of thresholding, which is in a way kind of like a 2-class clustering problem, either you're dark or you're light, right? To find out what are the darker shaped things in this subcluster, right? So this kind of thing is definitely a useful tool in things like segmentation. And certainly, if you take my image processing class, there's a fun algorithm called superpixel segmentation, which is kind of a cool way of making like a stained glass looking version of an image. Anyway, so this is the fundamental idea. And even though I'm illustrating this in 2 dimensions, it should work in 10 dimensions or 100 dimensions, right? Places where it's a lot harder to visualize what the cluster should be in the first place. Okay. So let me stop and ask questions or comments. Yeah.
Like with that hard case, because you do have a lot of overlap, and it's not really clear like which points are belonging to which cluster. Are you having a lot of error where the algorithm is classifying something that was like 1 point or
Right, so let me head you off there, right? So there are no labels in this data, right? So all we see are unlabeled black points, right? So there is no classification error because there are no classes, right? The only classes that are here are being discovered by the algorithm, right? So yes, to kind of give you a little bit of a preview though, so let's suppose that I did actually have labels on these points. Because believe it or not, I thought about that question before we came in today. So if I did have labels on these points, so say that these points were actually generated by some sort of process like this, right? So here, now I could look at these clusters and I could say, how well did I do, right? But now I'm talking about a different problem. So in regular unsupervised clustering, there are no colors to the points. They're all just undifferentiated black points. But in general, the problem that we care a lot about solving in machine learning is this problem of trying to find boundaries in space that separate out the classes as well as we can, right? And this is also kind of a prelude to thinking about like, okay, so, clearly there are some things, so what do we learn from this picture just as a preview? One thing is that, maybe straight lines are not the best boundaries that we could draw, right? The other thing is that when the points are drawn from random data, we are unavoidably going to have overlap between the distributions of the classes. And the thing that we can do is just do the best that we can, right? But like I said, I don't want to dwell on this figure too much because really we don't have those colors in our unsupervised problem. We only have black points, right? And only you as a human is looking at this and saying, okay, there are lobes to the data, right? So certainly you as a human could look at the easy case that I drew and say, oh, there are clearly 2 clusters in this data, and if I ask for 3 clusters, that's too many, right? Like I don't need to have the 3rd cluster. I could just do it with 2 clusters, right? So we'll talk about that, some more in terms of like when do I stop doing the clustering? Because I can always do better in terms of the J value with more clusters, right? So I can always add more clusters. I mean, the limiting case is that I have n clusters, and then everyone has 0 error because everyone's part of their own cluster, right? But that's not exactly what I want, right? Probably what I should do is, again, coming back to this issue of what you call regularization, right? Where I say, okay, I'm going to have a cost function that is the sum of the clustering error, the sum of the square distances, plus some penalty that says how many clusters do I have, right? And that way I trade off the number of clusters with the quality of fit, right? So this is a good illustration of some of the things that you might think about. And I think that maybe I will get into that a little bit on the homework, right? Kind of asking you to apply some techniques to understand what is the right number of clusters that you should ask for. Okay, other comments or questions? So before I forget, let me just write down what I said earlier, which is that, basically, k-means clustering is useful in kind of image processing as a means for segmentation. And also a good application is basically in communications, but also this idea has been adopted to machine learning, signal processing. This idea of basically representing a point by its cluster, you could think of as a form of quantization, right? So this is also known as vector quantization. So, for example, if I go back to my picture here, suppose I was an image processor and I wanted to code this image with less than 24 bits per pixel, right? Because I usually have 8 bits per red, green, blue channel, right? But I look at this, I say, well, really, there are only 3 clusters here. And so if I was in some sort of resource constrained scenario, what I could do is just kind of represent this image by kind of like the equivalent, paint by numbers image. It says, which cluster am I in? And just send for each pixel a label along with the cluster center that gives it a color, right? This could dramatically save on the amount of space it took to store this image, for example, right? So in image compression, this kind of process also has some sort of a use. Okay, so now what I want to do is I want to relate this k-means algorithm to something we touched on in the last lecture, right? So last time we basically talked about what was called, well, we talked in general about probability density functions and density estimation. We talked about how do I estimate the best Gaussian that corresponds to some data, right? I look at it, the sample mean, the sample covariance, and now I have the mu and the sigma. But we know that some data, like the pictures I showed you earlier, those don't really look like great Gaussians, right? So how could I fit what's called the mixture model to that type of data? Well, it turns out that the mixture model fitting process is very similar to this k-means iterative process. So k-means is related to the process of fitting a Gaussian mixture model to data. Just a reminder, what is a Gaussian mixture model? So the Gaussian mixture model PDF looks like this. It says I have k normal densities, each of which has a mean and a sigma. And so these pi's here are basically what we call mixing coefficients. And they sum to 1. And so the Gaussian mixture model basically is, and actually, if I'm being honest, the way I generated the data in the first place for these problems was via a Gaussian mixture model, right? So if I look at the, I know you can't see what I'm typing, I'm just setting something up. So if I look at the original data that I made for this easy case, this is in fact sampling from a Gaussian mixture model, right? Where half the points are from a Gaussian that is centered over here, and half the points are a Gaussian that's centered over there, right? And so kind of what I want to do is I want to take the data that I have and I want to recover, okay, what is the relative proportion of points in each Gaussian, and what are the corresponding means and covariances, right? So that's the problem of fitting this density. Okay, so, and the kind of difference between this problem and k-means is that, if I look at the kind of medium case, so the medium case, actually, if I show you the labels, if I cheat and show you what the labels are, I can see that the way I generated these points, there is a mixture kind of in the middle, like near the origin, where I could have generated a point that came from the red distribution in that position, or I could have generated a point that came from the green distribution, and it's impossible to disentangle them because they overlap, right? So that's kind of the part that makes this interesting, is can I kind of take a black cloud of points, like you saw before, and kind of tease it out into classifying, where the Gaussian ellipses are that overlap this picture. Okay, and so let's talk about how that works. So let me just say that, so what does that mean? It means that every point then here is not assigned to a single one of the Gaussians, right? It's not a hard assignment. It's more what you call a soft assignment, meaning that what I do for every point is I basically have a vector that I can think of like a PMF that says what's the probability that this point was generated by that Gaussian. Right? So for a point like way out here, that probability vector is probably going to look like, 0.999 for the red distribution and 0.001 for the green distribution. But somewhere over here, I may have points that have kind of like half and half, right? I don't know which distribution generated, and in some sense it doesn't matter. So what I'm trying to do is I'm trying to decide not a hard membership per Gaussian, but a soft membership. And that's the basis of this algorithm we're going to talk about called the EM algorithm. So let's go back to the notes here. So the idea is to fit data, again, this is unlabeled data, so it's an unsupervised problem, to a Gaussian mixture model. And so the key difference, which I just said in words, is that we're really doing what's called soft assignment versus hard assignment. And we're definitely going to come back to this kind of concept when we talk about things like logistic regression in a few weeks, where the idea is that we're kind of implicitly assigning a probability vector to every point that says, what's the probability I came from each of these distributions, okay? So the other thing is that, kind of one thing to realize for k-means is that, also the k-means, clusters had kind of an implicit circular shape. Meaning that, when I talk about this distance, like xn minus mu k, that's kind of like saying that I'm looking at the Euclidean distance where I don't care, like all the points on this circle have the same Euclidean distance. All the points on this circle have the same Euclidean distance, right? So the distances that I'm measuring in the d-dimensional space are all just like what you call isotropic, right? I don't care about direction. But with Gaussian mixture models, the kind of covariance matrix lets us have, kind of distances in space that kind of are defined by the contours of the PDF, right? So again, if you took probability with me, we kind of drew these like equiprobable contours, where here, this is like saying the variance in this direction is bigger than the variance in this direction, right? So for example, my sigma could look like, 2001, something like that, right? That's like saying that there's more variance in x than there is in y. Or I could have, and so this is basically a diagonal covariance matrix. Or I could even use a generic, covariance matrix like this, where my sigma is basically kind of like, not diagonal. You'd call this like the kind of, full covariance matrix situation, right? So in the pictures I drew, the kind of implicit contours that I draw are not necessarily going to be circles in the plane. They're going to be tilted ellipses, okay? Okay, so if we kind of carry on what we talked about last time, the thing that I should do to fit the PDF to the data would be maximum likelihood estimation, right? So remember last time we basically said, okay, I've got my PDF and I've got the variable that I want to find. I write my kind of likelihood and I take the derivative and I set it equal to 0. That's how I got the maximum likelihood estimate of the Gaussian mean last time. So, basically, ideally, we want the maximum likelihood estimate and at some point, I'm just going to start calling this like the ML estimate of the GMM parameters, right? So what I would have to do is I'd have to say, okay, I want to minimize the log likelihood of the probability of seeing my data points given the pi, the mu, and the sigma for all of the mixtures, right? And so, I could say, okay, well, hopefully this data is independent, right? Which means that I can decompose the log, I can decompose this thing into the product of all of the individual probabilities, and that turns into a sum, right? So that's not so bad. I could say under IID conditions, this is like saying I just look at the probability of just seeing this guy. But now if I write down what is this probability, well, this probability is what I wrote down a couple slides ago. This probability is like saying I have the log of the sum of this thing. And this is where I have a problem, right? Because as you remember from calculus, logs are lots of fun when you have a product of terms, right? But logs are not any fun when you have a sum of terms, right? There's no way to kind of take this log of a sum and kind of like reduce it any further, right? And so if you imagine trying to take the derivative of this thing with respect to all the parameters simultaneously and say equal to 0, well, that's not a very easy mathematical problem, right? Luckily, we can get at good estimates of all these parameters using an algorithm that is very similar to k-means, this kind of idea of seesawing back and forth between updating different things, right? And so that algorithm is called the EM algorithm. So, so this is hard to minimize. Or let me just say, can't minimize in closed form, meaning that, if I had one Gaussian, I could give you a formula for mu and sigma, right? But I can't do that when I have this sum here in the middle. So, luckily, we can solve this problem with something like k-means. So, luckily, we can apply a k-means like strategy called the EM algorithm. And the EM algorithm stands for expectation maximization. And so, oddly enough, this is where the E and the M from my explanation of k-means come from, right? So the steps are very similar, right? So first I have to have some sort of initialization. And then I'm going to do this kind of seesawing back and forth process, right? So similar steps. So the first thing to do is I have to initialize these parameters. I've got the mixing parameters, I've got the mu's, I've got the sigmas, right? So an easy thing to do to initialize that is just to actually do k-means on the data to give me basically a set of cluster centers and memberships. Then once I've got the memberships, I fit a Gaussian to each of those set of points, right? So just to write down what I just said, I could do k-means to data, and then I could fit a Gaussian to the points in each cluster. And then, that gives me the mu's and the sigmas, and the pi's, which are basically like the proportions. I can basically just measure those from how much data was ended up to be found in each cluster, right? So the pi's are the proportion of points in each cluster, right? So that's an easy way to kind of start off. And so now what I'm going to do is I'm going to do this kind of like back and forth step, right? So I'm going to, well, what do we do in k-means? In k-means, we assigned points to clusters, right? So I'm not going to do a hard assignment. I'm going to do a soft assignment. Is that a question? No. OK. So what are the E step and the M step? So the next step I do is basically, instead of hard assignment of points to Gaussian, I fix these things that define the Gaussian mixture model, and I evaluate what's called the responsibility for each data point. What is that? I'm going to write it down like this. First, I'm going to write this down, and then I'm going to explain what it means. So this is like saying for each of the, so for every point I have a vector, right? Playing the role of this one hot binary vector from k-means, but except this vector is no longer going to be binary. So this is going to be a vector that sums to 1, but is not binary. Right? This is like saying the numerator of this vector is like the likelihood of the kth Gaussian evaluated at the nth data point, right? And the denominator is basically the whole mixture model evaluated at the data point. So it's kind of like saying how much of the likelihood is how much of the likelihood is the kth cluster responsible for, is the kth Gaussian responsible for, right? So I have a whole likelihood, and that likelihood is actually just the sum of a bunch of sub-likelihoods coming from each of the k Gaussians in the mixture, right? So this number could be like, 0.4, 0.3, 0.2, 0.1, if I had 4 Gaussians in my mixture. That would say that the first Gaussian was 40% responsible for generating that point. And this, so basically every Gaussian, no matter where it is in space, always has some non-zero probability of generating a point, right? So none of these numbers are going to be ever 0. But if you're close to the mean, if you're right in the middle of that tight contour, then that number is going to be high. And if you're far away, then that number is going to be low. And this is basically like a kind of a rebalancing of that vector so everything adds up to 1. So if any of you have ever done any machine learning before, it's like doing a softmax on the vector. We'll talk about softmax further. Don't worry about that. Yeah?
So the first element of that vector corresponds to the fourth, to the fourth cluster? Or?
So basically these are like, these are like the 4 Gaussians in the mixture. And this is saying at this point, Gaussian number 1 kind of is responsible for 40% of the likelihood. Okay. Other questions or comments? Now again, I'm throwing a bunch of math on the screen, and again, this is why we have a book. This is why you have to do some reading outside of class. I'm not expecting you to absorb it all like 100% the first time. The EM algorithm in particular is probably like, I flip forward to like chapter 9 or 10 of the book to get to this material. So you have to kind of do a little bit of reading on your own to make sure you understand this stuff, right? So the way to interpret this vector gamma is basically like the probability that this point arose from mixture K, right? So this is like the probability that point N arose from mixture number K. How much does mixture K explain what I saw at that point? Okay. So now these gammas are playing the same role as the memberships, except they are soft memberships and not hard memberships. Okay. And so now you should kind of be able to anticipate what's going to happen next. Now we're going to fix these memberships, and I'm going to re-estimate what are the parameters of the Gaussian mixture model, and I'm going to seesaw back and forth, right? So the M step now is basically saying, to re-estimate the GMM parameters given the responsibilities. So I have to evaluate three things, right? The mean, the sigma, and the pi, right? So the mean that I update, the new value of this mean, is going to be basically like the average responsibilities, like this, right? Again, this kind of makes sense, right? So if I had hard assignments, then this would just be like taking the points that are in the cluster. If I have soft assignments, this is just saying, well, I'm going to add up the first element of that vector for all of the points that I have, right? And some points are going to, contribute more to Gaussian number one, and some points are going to contribute less. And it's kind of like a weighting factor on how much of x do I include when I compute the mean. It's like a weighted average of the x values to compute the new mean, right? So it's just like a weighted average is one way to think about this, where the weights are not equal, but they are proportional to the responsibilities. In a similar way, the covariance matrix, I also update with kind of like, and I'm going to say also this nk is basically, I should make a notation here. So nk is kind of like just this by itself. So I take this number. This is kind of like, in a very hand-wavy way, like how many points are in this Gaussian, right? Except this number is not going to be like 4 or 8. It's going to be like 16.2, right? Because it's going to be the sum of a bunch of fractional numbers. So I'm kind of like, that's my kind of like, number that I put here. In the same way, I compute kind of like the sample covariance. This is not that different than the formulas that we used last time for fitting a single Gaussian. Right? This is going to be an n by n covariance matrix. And then my updated mixtures are going to basically be, the proportion of data. So this is kind of like the, effective number of points assigned, I'm going to put assigned in quotes, to k, right? So basically they're just kind of like, in a way, they're just like weighted sum versions of the formulas that would make sense when these numbers here are fractional and not binary. So it's kind of like a softening up of the hard assignment. And that's it. So basically, we seesaw back and forth between updating the mixture model and updating the responsibilities and go back and forth, right? So we, alternate the E and M steps until the, log likelihood, stops changing much. Or we reach some number of maximum iterations, the same as we kind of had before, right? And so what we want to do is, again, here, as you're going to see in the numerical examples, there's definitely no guarantee that the first time I do this, I'm going to get the best set of Gaussians, right? Hopefully there won't be too much moving around, but it's certainly true that you may want to run this Gaussian mixture model fitting process, this EM algorithm, 5 times and take the one that has the highest likelihood of the data at the end of the day, right? So, as before, best practice is to run several experiments with different initializations and take the best. meaning the highest likelihood of generating the data, right? I.e. highest, log likelihood. Okay, so let's look at this example numerically, or let's look at this process numerically, okay? So if I go back to my MATLAB notebook, so here I wrote a function that I called, first of all, I'm going to just get rid of this guy because I don't want to have this come up on the screen all the time. All right, so I wrote a function called Gaussian Mixture Model illustrate. So here, let me write down on MATLAB again. So the workhorse in MATLAB for this process is called fit GM dist, right? Fit Gaussian mixture distribution. Where basically you specify data and you specify the number of Gaussians, and it goes off and runs this EM algorithm, on its own, right? So so let's take a look at that, and I have to remember how did I what did I call these input arguments? Let me just direct this for a second here. Okay, so let me go back to this. And this is an illustration of fitting, let's take the easy example and fit one Gaussian mixture model to it, right? Right? Fitting one mixture model is the same as just the same mu and sigma estimation that we talked about last time, right? So I can see that here, this kind of stands to reason, right? It kind of draws this ellipse where these are contours of equal probability so that, it tries to hit as much data as it can, right? Now, this is not obviously to human eyes the best fit for the data, right? Because there's lots of points in the middle here that the mixture model, well, the single Gaussian would say that these points here have really high likelihood, but there are no points like that in the data, right? So if I were to fit two Gaussian mixtures, well, then life is much better, right? This looks much more like what a human would do in terms of deciding whether these were, one mixture or two mixtures, right? And then I could say, well, what happens if I would ask for three mixtures? Well, for three mixtures, this is again, I got two Gaussians here that kind of slightly overlap, right? To maybe give some help to the fact that maybe that data just happened not to be super elliptical, but maybe there's a little bit more on one side. But one thing to see is that if I keep on running this with different random seeds, I should get, so here, for example, this is another random run of this fitting algorithm where the second Gaussian on the bottom is now much smaller and off to the side, right? That probably has less likelihood than the other one did. And I'm sure if I keep on running this, see here, now I got two Gaussians on the top one, right? So you shouldn't just take the first output that comes to your hand, right? You should probably run this a few times. And I think actually probably inside the function, you can probably specify the number of times you want to run it behind the scenes, and it will give you the best one, right? Now, if I apply this to my slightly more tricky data, right? So if I apply it to, my medium-sized data set, so here, again, this data set doesn't look too bad. And actually, so here, I can scroll down and see that it's giving me the mean of the data set and the mixing proportion, which is basically 1, right? Because there's only one Gaussian. If I ask for 2 instead here, what I see is this. And this is actually the power of a Gaussian mixture model, right? Because here, it's able to fit these two overlapping oriented ellipsoids. And this is what it gives me. It says that, I am about a third of this one Gaussian and about 2/3 of the other Gaussian. And that's actually very close to how I generated the data in the first place, was this 2-to-1 ratio, right? So I can see that it's actually done a pretty good job of discovering, one of them I can see was 0 mean, right? Except the mean is estimated is not quite there. And the other one, the mean was 1, 2, and it's gotten pretty close to that also. So I can see that actually it did pretty well. And even on the harder data, the one that looked like the 3 lobes of data. So here, This is like the best fit with 2 Gaussians, which looks, okay. And then this is the best fit with 3 Gaussians, which looks, even better because it kind of has this like satellite out off to the left. And I can see here that if I look and see what the mixing coefficients are, like I did generate this data also with a fraction of basically half of the data is from component 3, a third of the data, or 0.3 of the data is from component 1, 0.2 of the data is from component 2. So actually, it did a pretty good job of discovering these underlying mixtures, even though the data is all overlapping there in the middle, right? So that's a Gaussian mixture model. So, and actually, I think I can see here. Let me just see if I made a function. So here, before I go back, let me say that you gain a lot of what I would call representational ability by letting these Gaussians be diagonal, right? That is to say, full covariance matrices. Because if I only allowed kind of axis-aligned ellipsoids, my representation would be worse, right? So if I, for example, look at, let's go back to this guy. So here, this is like the full covariance fit. If I were to say, only give me diagonal covariance matrices, then my ellipsoids are kind of forced to be kind of like axis aligned, right? Meaning that I have less representational ability, but also I have fewer parameters, right? Because a diagonal matrix only has values along the diagonal. A covariance matrix that's full has diagonal plus everything above the diagonal, right? So it kind of depends also on how much, in this day and age, it's not like you're limited by computational power, but it's kind of a question about like, how complex do I want my model to be, right? The simplest thing would be to have a diagonal matrix that had all the same values along the diagonal. Next step up is to say, okay, I'm going to allow you different variances along each direction. The final step is to say, okay, I'm going to let you have correlated values between the features, right? So let's look at, well, actually, it doesn't really matter. So I also made like a little kind of verbose command. So you can actually, when you're fitting this mixture model, get, kind of like this, iterative number of steps that shows you that the negative log likelihood is getting smaller and smaller, right? Which is what we want. So this is kind of like saying that what I'm doing is I am, starting with some value that's not so great, and then I get smaller and smaller, and then I end up with, this set of fitted Gaussians after 65 iterations, right? Now, it could be that if I were to have, some very mixed up data, that my maximum number of iterations by default might be exceeded, right? Maybe I have to have 100 iterations or 1,000 iterations, right? So again, you should always kind of like look under the hood of your numerical software, but instead of taking it for granted, right? Because I noticed that one of my students was just like, fitting the GMM once to our data, and we were even thinking about like, did it even converge, right? Or is this the best thing to do? Should we have run it a bunch of different ways, right? So it's always worth looking at kind of like making sure that your results have converged, making sure you can't do any better by running it again, that kind of thing. A lot of these algorithms that we're talking about are iterative, meaning that you get a different answer if you run it again due to random choices of initialization. Okay. Stop and ask questions or comments about this. Yeah.
Is there what makes this kind of better than k-means, or is it better than k-means?
It is better than k-means. So let's think about this. So for one thing, the k-means decision boundaries that I draw, well, okay, it's better than k-means because of the fact that I can kind of have soft assignment of points to clusters, right? I mean, definitely, I could use these Gaussians to do hard clustering if I wanted to, right? So let me actually just say that. So what I could do is we could also use a fitted Gaussian mixture model to do hard clustering by basically evaluating which mixture has the highest responsibility at each point. Right? That's like saying what I could do is now I could take not just the points that I clustered, but any point in the world and ask, okay, so which of these Gaussians is most responsible for a point in this location, right? If I did that, then I could take this picture and I could color it in by that region. And in fact, I did that. So here, so here again, I'll turn off the verbose part. Why did that not do my, oh yes. So, sorry, let me go back and I basically made a clustering version of this. So if I wanted to cluster using the GMM, what I could say is I could give me 3 clusters and use the GMM instead of k-means. Now what you see here is that the cluster boundaries, right, the region boundaries of what gets assigned to each cluster are not as simple as they looked before, right? So you can see these are more like curved lines and different things. And of course, I'm going to get different, I'm going to get slightly different look depending on the random initialization I have for the Gaussians. Like, so here's another one, right? But here's a kind of example where the green boundary kind of like does this little dip right in the middle instead of being just like a straight line like a Voronoi diagram, right? So the idea is that, the implicit decision boundaries, if I were to think about this as a clustering algorithm, would be more than just simple straight lines, right? And that's going to be a big deal when we talk about classification coming up in future lectures, is basically, yes, I want to draw, lines between classified points, and then I'm going to think about what is the best way to draw those lines. We're going to spend a lot of time actually thinking about what's the best way to draw the division boundary between 2 sets of points with a straight line, and then we're going to generalize that to lines that are not straight, so curved lines through the space. So again, we didn't, I colored these points in because I know when I made this data set that I had class labels, right? But in practice, I don't have the labels. I just have the clusters. And so in practice, what I have is this, right? Where I'm just going to look at my data points and I'm going to use that to make these representative regions of space. Again, with this one, you might kind of be a little bit like, well, that doesn't seem so great. So for example, if I were to just look at the 2-dimensional boundary for this, here, the boundary isn't a straight line anymore. It's kind of like a curve, kind of due to the fact that the fitted Gaussians are not like axis-aligned Gaussians. They're kind of slanted ellipses, right? And that kind of gives this thing a little bit of a tilt, right? So hopefully that kind of gets at the basic idea. Okay, other questions or comments? So one thing I want to say is that, and again, with 5 minutes left, we can't go into it too much, but let's just say that fitting a Gaussian mixture model is actually a special case of kind of like the full EM algorithm. Right? So typically, the easiest application of the EM algorithm is to the Gaussian case, and that's why I gave you those equations that I think are pretty straightforward to understand, right? But in general, the EM algorithm is used in a lot of more advanced study for signal processing in a way that is like not exactly what you saw, right? So kind of the idea, just for those of you that are interested, is something like this. The idea in general is that we have a joint distribution where I have something like this, where these are observed variables. These are what are called latent variables, which are not observed. And these are basically some sort of parameters we want to estimate. And so the GMM setup, basically the latent variables in some sense are the unknown Gaussian that generated that point, right? So in theory, for my data set, I knew that there was a latent variable that was binary. It said which of these Gaussians did my cluster, which of these Gaussians did I use to generate that point? I know that data because I generated it myself, but in a real machine learning problem, you don't have access to that. That's like a hidden variable that you can only estimate, and the gammas are our attempt to estimate that as closely as possible, right? And so basically the idea is that I have this distribution, but in general, we don't observe the z directly, and want to maximize this with respect to theta, right? That's like the general setup, is like saying, I want to estimate my parameters given my data. That process would be easier if I had access to this latent variable z, which I don't. And the EM algorithm is kind of a way of using the latent variable estimation kind of in the middle to make this problem easier. And I'm not going to write this down in some detail. If you're interested, this is in Bishop's book, chapter 9. If you want to talk about the full EM algorithm, that's where you'll find the details. But for our purposes in this class, just knowing how to estimate the Gaussian mixture model and know that it's an instance of the EM algorithm is fine with me. Okay, questions or comments about anything? All right, so next time we're going to talk about Bayesian decision theory, right? So that's going to be like, okay, our first step of classification. So it's like saying, okay, well, suppose that I had fit a PDF, Gaussian or Gaussian mixture model, to each of my classes, then how would I make the best decision between them, right? That's a pretty classical problem that, like I said, I hope you've already seen in hypothesis testing when you do probability. So maybe a little bit of review for probability, but I think it's still good to do. All right, that's it. I'll see you on Thursday.